7. Okay, all right, we're recording. I think we're good now. Okay, here we go. So here's where we left off last time. We just barely scratched the surface of section 2.6, and basically all I did is remind you of some already established facts about partial derivatives. So partial derivatives are slope of the graph. That's one important interpretation. They're a multiplicative factor. They're what you multiply by input change to get output change. Now, both of these interpretations come with an important asterisk. You get the slope of the graph as you move in the direction of that standard basis vector. You get the multiplicative factor if your movement is in the direction of that standard basis vector, right? So this idea, as we have it conceived right now, only applies to standard basis vectors, and that's a very important asterisk for the moment. Again, another couple of quick observations I sort of waved my hands at is that this is just a different way of writing the definition of a partial derivative. You can see right here in the construction that because we're looking at a plus tv there, well, that means that we're at the point A, certainly when t equals 0 anyway, we're at the point A. And you can also see from this right here that we're moving with velocity being EI. So in other words, we're at a certain point and we're moving in the direction of exactly one coordinate variable. That's the idea of a partial derivative. And in that scenario, we're looking at how fast the function changes. Right, so just a rewrite of the definition. And another neat observation, and this is an easy one to see once you realize that this is a vector made up of all of the partial derivatives. Well, then when you dot product with a vector that's mostly zeros and has a 1 in a single position, that 1 is going to multiply by 1 of those partial derivatives, and thus you will get that corresponding partial derivative. Okay, so several observations about partial derivatives, and now I'm going to make an outrageous assertion, seemingly outrageous assertion, that I don't have to restrict my attention just to standard basis vectors. I can do this in the direction of any other unit vector. Now that's an outrageous suggestion, right? I mean, where do you get that from? A lot of the arguments that I just made seem to depend on this being a standard basis vector. Where do I justify this idea that I can pick any unit vector? So here, that's one thing I want to talk about here a little bit. And let's see if I can get this to cooperate. There we go. So just going to zoom in on this for the little bit of clean page to work on. Here's the scenario. We've got the XY plane here, let's say, and we have an x-axis and we have a y-axis, right? And as a result of that, well, we have these standard basis vectors, E1 and E2. And they have these seemingly unique features that, well, they, mostly zeros and 1 in a single position. They could point along the coordinate axes, and they seem really official and canonical. And here's the thing. They're not. They're arbitrary, believe it or not. And the reason why is they come out of an axis system that is itself arbitrary. Right? So if you think about it, what you start with is a plane in which you're doing business for whatever reason. Like maybe this represents the land in the vicinity of my house, or maybe this represents some other region of space that I'm interested in describing. Why did I feel compelled to set up my axes like that? There's no particular reason it's good that they're orthogonal, right? But there's nothing magical about vertical. There's nothing magical about horizontal. They're just directions, right? So I could just as well, right? In the vicinity of my house, I could just decide, alrighty, well, then I'm going to set my coordinate axes like this. those are going to be my coordinate axes. This will be the x-axis, this will be the y-axis, and in those directions I have two corresponding unit vectors, and now guess what? Those are now standard basis vectors, just using a different orthogonal coordinate system. So that's the big idea here. I mean, there's this temptation to say that standard basis vectors are, intrinsic to your situation, but they're not. They come from an arbitrary axis system that you set up in a way that doesn't matter, right? So just a reminder now, here's our situation. We have an x-axis and we have a y-axis, and we correspondingly have standard basis vectors about which we now know cool facts. And what if I were interested in a unit vector pointing in a different direction? It's not a standard basis vector. I can't interpret it like a standard basis vector. But it could be, right? I could say I'm just going to set up my axes like this, and now, that's now a standard basis vector. So that's the kind of nice observation that you should expect then. Let's see here. Let me hit that button. We should expect that all these properties that I've described up here, as pertains to standard basis vectors, should apply to all other unit vectors as well, because any unit vector could have been a standard basis vector. Okay. All right. So here's the corresponding results then. And this is just taking the same interpretations. Take any unit vector. Now, it is important that it be a unit vector, right? It's going to change things. You're going to have scaling problems if you don't restrict your attention to unit vectors. But for any other unit vector, we can look at this construction that defined our partial derivative. That's going to define something kind of like a partial derivative. It's going to be computed by that exact same formula by which we computed our original partial derivatives, right? I just have to be careful. Let me use my colors a little bit more carefully. I have to be careful that whatever unit vector I pick, that unit vector then needs to go where there previously had been standard basis vectors. So what am I going to call this construction? Well, I can't call it a partial derivative. I mean, let's face it, as arbitrary as coordinates are, they sure are handy, and we don't want to be constantly doing change of basis. It gets a little unwieldy, right? So I'm not going to call these partial derivatives. I'm going to call them something else, but it's important that y'all keep in mind that this thing that I'm going to call them is just for semantical convenience. They are morally I hesitate to say the same, but they're basically the same idea as a partial derivative. So it's what we call a directional derivative. Here's the notation that we use. We do have to say where we're computing this directional derivative, and we do have to say in which direction are we computing the directional derivative. Okay. And again, we get these same interpretations. It's the slope of the graph as you go in that direction. That direction, that could have been a standard basis vector. And it's a multiplicative factor. What you multiply by input change to get output change. Again, assuming that you're moving in that direction. So, very important concept, and I think it's a little bit weird when you first come across this point of view of any unit vector could have been a standard basis vector, and I know that's a strange point of view, but it's very fundamental if you really think about it, and ultimately not that deep a point. So anyway, I hope this is a satisfying point of view. Now there is one little clarification I want to make, and that is this multiplicative. That's not the color I wanted. This multiplicative factor. Let me momentarily scratch that out for dramatic purposes. And keeping in mind, when I say it's a multiplicative factor, it's what you multiply by input changes to get corresponding output changes. And now let's just think through, well, what notation should we use, right? Just looking at these equations down here, if I can get them to, there we go. What notation do you think we ought to use for the thing I multiply by ds to get df? The thing I should multiply by ds dt to get df dt? And I think there's a pretty obvious, I'll say an obviously motivated notational option. And that is, how about we call it, colors. How about we call it df ds? Now, again, that's just notation. It's not a fraction. I'm going to write it like a fraction because it behaves like a fraction sometimes, such as now. So it's convenient. It's also very standard. You're going to see this all over the place, right? And it's a little cringy in a way to write things like a fraction that aren't fractions, but that's the world we live in. So we just have to get on board and learn to like it. Okay. All right. So, so that's this idea, directional derivative. Let's see some examples how we will use this new tool. Here we go. I have a function given, multivariable function. I'm interested in the graph of that function. Keep in mind, graph is this very specific construction, right? Graph doesn't mean whatever picture you should happen to prefer to generate, right? Graph is constructed in this very precise, specific way. So if we're looking at the graph of that given function, and if the question is, how should I compute the slope of the graph? Oh, well, that's one of our immediate, already established interpretations of directional derivative. Right there, boom. Slope of the graph, directional derivative. Right back here in, directional derivative, slope of the graph. So cool. All right. So I've got an answer. I've got a foot in the door. I'm going to answer this question by computing a directional derivative. Now there's a nasty little asterisk here. You do have to be careful with the following. The vector that you put here to define your direction, the thing that you will use in that part of the definition, the thing that you will eventually dot product with, that vector has to be a unit vector. Very important. Or else problems, and we'll talk about the problems that come up if you get this wrong in a couple of minutes. But so make sure that's a unit vector. Notice the vector I was given is not a unit vector. So I cannot just put a v in there. Right? Directional derivative, as we're doing it in this course, is defined only for unit vectors. So, okay, right, well, so that what that means is I've got to identify, after all, the question said the direction of that vector. That means the direction that that vector is pointing. And it's actually not hard to identify what the direction is, represented by a unit vector. If you want a vector that points in the same direction but is a unit vector, you just take that vector and divide by its own magnitude. Old news, right? That's from way back. So we do that. Now we have our direction, aka our unit vector, aka what I'm going to dot with, and now it's all plug and chug. Everybody happy? Cool. All right. Here's another example, and this is another pretty straightforward example. But we have temperature as a function of position, so multivariable function, right? Several input variables, one output variable. And let's see here. The question says, what is dt ds? The question is asking how fast does temperature change as I move in a certain direction. Again, the direction of a given non-unit vector, and I will then have to make a unit vector. We'll get to that part in a second. But how do I compute the rate of change of temperature with respect to distance traveled? How fast is the function changing per unit distance as I move in some direction? Well, again, that's an immediate interpretation of directional derivative. Again, right here, let's see here. I got my colors the wrong way. Df ds that multiplicative factor is the directional derivative. Right? So if you've been asked to compute df/ds, well, you've been asked to compute directional derivative. And again, I'm going to compute it with a dot product with the gradient. So, okay, back to here. Dot product with the gradient. And again, it's pretty much all over. So let's see here now. There's algebra to be done, of course. You've got to take your function and you've got to take the appropriate partials to compute your gradient. And the gradient ends up being this. Again, that's just partial derivatives. Y'all can check me on that. And there's one of the problems with, by the way, with this style of teaching that I do is I kind of wave my hands at a certain amount of rubber meets the road computation, detail devils, right? And you do have to be very careful with that and make sure that you can do those details, because that's how the as they say, the rubber meets the road. That's what makes the car go, right? No rubber, no car. It doesn't matter how good your engine is. So make sure that you're good with those details. And then again, we have this issue of we want the direction that this non-unit vector is pointing, right? How do we find a direction? Directions being represented by unit vectors. Well, we've got to find the unit vector that points in the given direction, and we do that by taking the non-unit vector and dividing by its own magnitude. Again. Okay, and everything else is computation. Okay, how we doing? Everybody on board? Okay, now I have a cultural note that I have to make. This is very frustrating, but it's also funny. I am sorry to report that not all books, not all users of the idea of directional derivative agree on the definition. There is an important disagreement, and it is important, and it'll cause major problems if you're not careful about it. But the good news is it's easy to be careful about it. Right? So anyway, the alternative interpretation of directional derivatives is to take the unit vector requirement and just get rid of the unit requirement. Right? We'll just say whatever, any vector. And that we can talk about a directional derivative for any vector. Now, that messes things up a lot, and I'll spare you all the details, but here's the punchline. If you remove the unit requirement, let's see, let me do it like this. If you remove the unit requirement, you lose property 1. It no longer represents the slope of the graph. No surprise, right? I mean, the whole idea of it being a unit vector is so that we can say it could have been a standard basis vector had we just set up our axes the right way, right? So that interpretation's gone. This multiplicative factor interpretation, gone. Everything, in fact, down here, all gone. You lose all of those interpretations, but you retain that this thing defined for non-unit vectors still computed by that same formula, and it's still computed by this same convenient dot product. And it's still a fundamentally natural thing to want to talk about. Give me 2 seconds. Even if you have a non-unit vector, look, it's still perfectly reasonable to talk about, well, I am at some point A, and I am moving with some velocity V, and I would like to know how fast the function's changing. That's a really natural thing to want to talk about. And removing that unit requirement allows you to just write that thing down, and we give it a name and a notation. It's very handy. And a lot of people use this as their definition. A lot of mathematicians in particular go with this. All else being equal, practical considerations aside, I would put myself in that camp. if it was up to me, right? Anyway, there are pros and cons. It's good to be familiar with both of these concepts. The problem, of course, is that this is a class. I owe y'all clarity on what I mean when I say certain words and write certain notations. And so in this class, we're not getting rid of the unit requirement. In this class, directional derivative. What is the highlighter? In this class, directional derivative, we use this notation. It's defined like so for unit vectors. Computed by that formula, does give me the slope, does give me the multiplicative factor, is a way to compute DFDS. This is the policy for Math219. Everybody clear on all that? And I just wanted y'all to be aware that outside of this class, clarify. Don't just assume that whoever you're talking to uses the same convention that this course does. Yes, go ahead.
For number one about the slope.
Yeah.
I was under the impression the slope is a direction and multiplying the direction by a constant doesn't change it.
Slope is a scalar. Slope is so if I say, I'm moving in, oh gosh, let me clean up the picture here a little bit. If I am moving in a certain direction, right? So if I'm moving in that direction like that, that's a vector v, right? The slope says, okay, as I look at, I was trying to hit a horizontal line there. Focus. There we go. As I move in that direction, and that's just another horizontal line directly above, then I can look at the tangent line to my function, to my graph, and I can talk about the rise over the run. And the rise over the run is a scalar. Yeah. Is that cool?
Yes, I
yeah. Okay. Yeah. Good deal. Okie dokie. All right. Okay, so moving along, here's a related concept. This is a really useful idea. Important question that comes up a lot, and that is, suppose you have a multivariable real-valued function. By the way, all this stuff about directional derivatives, we typically focus on real-valued functions for this. Differentiable, real-valued, multivariable function. Reasonable question, looking at all directions I might move from wherever I might happen to be, right? So all the different possible directions represented by unit vectors, of course. We don't want to worry about the speed. We'll worry. Speed will come in at some later time. Just focusing on the various different directions I can move. Which one of those directions will maximize my directional derivative? And keep in mind, on this picture, the way I would represent directional derivative is by how fast am I moving in the output as a result of moving in a certain direction in the input. Right? So if you want to maximize, you want to make that rate of change as big as possible. Let's consider scenarios where that might be the case. My favorite silly example is I'm at the point A out in the woods and I'm cold. And I know what the temperature function is. Which direction should I go to get warmer? Right? You want to make that temperature increase as fast as possible. Right? Another scenario, maybe I'm mountain climbing and I'm at the point A on the map. And I want to climb the mountain. Well, one point of view on that is I should know which direction is uphill. Which direction will make my height, my altitude, increase as fast as possible, right? Very natural question. Maybe A represents not a location. Maybe A represents the current state of certain parameters of the business that I'm operating. And maybe F represents profit. Which direction should I start changing those parameters to make profit increase as fast as possible, right? So there are lots of natural interpretations. So it's a very important question. We're going to have to figure out how to answer this question. Now, one thing to keep in mind, this being a directional derivative, it does have a couple of different interpretations, and these different interpretations motivate different terminologies. So in particular, if I, for the moment, interpret the directional derivative as telling me how fast the function's increasing, then the direction, the one that maximizes, whichever direction it is that makes this as large as possible, wouldn't it be natural to call that the direction of fastest increase? It's the direction you go to make the function increase as fast as possible. So I think that's very natural terminology. Now, on the other hand, what if I were to take the point of view that the directional derivative represents the slope of the graph, which it does. The direction that makes my slope as great as possible, wouldn't it be reasonable to call that uphill? Right? But more common terminology, call it the direction of steepest ascent. Fancy talk for uphill. Does that make sense? Okay. All right. So another quick side note of a cultural point. The more common terminology here is this one. Direction of steepest ascent. You'll hear that all the time. I have a problem with this terminology. This terminology really only makes sense if you're talking about interpreting the function by way of its graph. It only makes sense if the value of the function actually gives you height, which means you're looking at a graph. And as I've complained before, very often, not only are we not always looking at graphs, very often you can't look at graphs. So this terminology is motivated by a narrow, arguably narrow scenario, narrow circumstance, right? So on the other hand, this is not. This terminology right here makes sense if in any context, really. There's no assumptions that, you have to be looking at it in a certain way. No, this always makes sense. So I personally prefer this terminology. That's the terminology that I gravitate towards right now, 2 seconds. I, however, will admit I was brought up using this terminology. I have a certain amount of habit in my speech patterns that I will say this just out of sheer habit. You'll also hear this terminology probably much more often outside of this course. But I want you to be aware of both. And again, I'm going to make every effort to use this terminology because I think it makes more sense in general. Yes?
Are we always looking at the positive direction of our vector?
So the question that we're going to ask here, and by the way, notice I haven't answered the question yet, right? But the question that we're going to ask, which one maximizes, yes, will always be about maximizing. Now, if you find yourself in a scenario where you want to minimize the directional derivative, no problem. You can either view the question in terms of a new function, which is the negative of f, right? Or, as it's going to turn out, you can take whatever direction maximizes it and just go exactly the opposite direction, and that'll minimize it. Yeah, that's right. Is that cool? Yeah. Good question. Okay, all right, so let's do it. How do we, did you have a?
Just a
yeah.
final
Yeah.
question, right? Okay, so df, ds, and the slope, functionally, mathematically, they're the same value, but
yeah, it's just interpretations. Oh. Yeah, that's right. So this and this will always be computed by the same thing. So computationally, they're the same. Yeah, it's just interpretation. It's a little different. Totally. Okay, so how do we answer this question? What is this ideal direction? And just to be kind of blunt about it, this is the thing we want to maximize. It's computed by that formula, which is a dot product. Dot products are always computed by that expression. Oh, wait a minute, my vector is a unit vector. That means that this factor here is 1. I don't need to write that down. It's 1. Right? We're restricting our attention to unit vectors. So really, this is what I want to maximize. And if you think about it, I can simplify this even further because I'm at the point A. I will eventually be moving, but I haven't started moving yet. I'm still contemplating which direction I would like to move. So at the moment, A is a constant. That means that the gradient vector isn't changing. The gradient vector is defined by the point. So as I contemplate various different directions that I might start moving, I'm still contemplating the gradient is the same for all of them. So this is a great big constant. So the question actually simplifies really nicely. At the point A and contemplating all your various different directions, if you want to maximize the directional derivative, you just have to figure out how to maximize cosine theta, and that's easy. You maximize cosine theta when theta, this angle between the two vectors you're dotting, theta needs to be 0. That's how you maximize cosine. Does that make sense? Cool. So how do I make that angle 0? Well, that's the angle between the gradient and the direction I'm going. If I want the angle between those two vectors to be 0, that's accomplished very easily by just going in the same direction the gradient does. Nice simple answer. What's the direction of fastest increase? Whatever direction the gradient points, that's the direction of fastest increase. Okay. All right. Yeah. Okay, next question. What is the directional derivative in that direction? Nothing to it. Again, the directional derivative is this dot product. Now, we've just agreed on what the vector v is. V, the direction that achieves that maximum, is the direction of the gradient. So you want to know what the directional derivative is? Okay, we'll keep computing here. And let's see here. We find ourselves looking at gradient dot gradient, which is magnitude squared. And then you get a nice little cancellation. And the answer is the magnitude of the gradient. That tells you what that maximal directional derivative is. Okay. So, nice rephrase. I'm going to sort of rephrase this in terms, not in terms of how the gradient is the answer to various questions, but I'm going to rephrase this as how the questions give interpretations of the gradient. So we have this thing called a gradient vector. The gradient vector points in a direction. Oh, it's the direction of fastest increase. This gradient has a magnitude. What is the meaning of the magnitude of the gradient? Oh, it's the rate of change, aka the slope of the graph as you go in that direction. So this is a monumental moment in our use of the gradient vector. Let me remind y'all that up until now, the gradient vector has been a notational convenience. I don't like writing down all those partial derivatives. It's just bulky. So we made up this shorthand just to spare us the inconvenience of writing down all the partial derivatives. It's just very clunky and tedious. But now we have a geometric interpretation of the gradient. Gradient is no longer just a notational convenience. The gradient is something whose direction means something. That's geometrically natural. It's something whose magnitude means something. Its magnitude is geometrically natural. It tells you how steep is the mountain, if you will. So nice little moment there, and let's see how applications of this work out. So there's a weird thing about this question that I'll get to momentarily, but first let me state the question. We have a certain hill, and it's in the shape of the graph of a certain function. So this function here, f, of course you can define the graph of f, and very importantly, graph means we're going to set z equal to the value of the function, thus giving us a three-dimensional picture, which in this case is what the hill looks like. Okay, so there's our scenario, and here is me. I'm sitting on the side of the hill, And the reasonable question is, okay, from that point, which direction should I go to go uphill? If I want to climb the hill, which way do I go? Right? Reasonable question. Now, let me talk about the awkwardness of the terminology and the notation here. How do I describe this location? In fact, here, let's step back and ask broadly, how do I describe locations in general on planet Earth? Longitude and latitude, right? Coordinates, 2 coordinates to describe, in some sense, this way and that way. And if you know longitude and latitude, then you know exactly where I am. Notice I didn't say anything about altitude, because that's obvious. If I say I'm at certain longitude and latitude, it's understood that of course I don't mean I'm at sea level. That would be 300 feet underground where we stand right now, right? Of course I mean on the surface, right? So the problem is then that I am actually on the surface, but in practice, day in and day out, we describe locations by map coordinates, namely just the 2 coordinates. That 3rd coordinate is for the reader, the interpreter, to obviously interpret correctly. Does that make sense? So a little bit of an awkwardness here. Again, I am actually at this point here. I am sitting above the point that I will describe this with. And just so you know, in practice, vast majority of the time, nobody goes to the trouble to distinguish and say, oh, the point's sitting above 1,3. Most of the time, as in life, we will just say, oh yeah, I'm at 1,3. Where are you located? Well, I'm at a certain longitude and latitude. That's how people communicate. The altitude aspect of it is obvious. So I have to make a big deal out of this because, again, this is it's an easy way to get confused. You got to understand when someone gives you XY coordinates, thus a point in the XY plane, it's your job to remember they're actually up there. Okay. All right, so that noted. Let's see here. The question says, which way is uphill? Cool. No problem. It's in the direction of the gradient. Now, how we answer how we describe the direction that the gradient points. Oh, and I guess I should put the check mark here. We do need to evaluate at the point in question. So it's the direction that this vector points. In this case, that being what that direction is, you could call that southwest. The idea being that the y-axis typically, when you're drawing maps, typically represents north. Right, so that would be southwest. You could also describe it by a unit vector. Do you have to turn this into a unit vector? Kind of depends on how quibbly your grader is, right? Really, ideally, in an ideal world, directions are represented by unit vectors. So yeah, you kind of really should. Will they count off if you don't? It's a question of how quibbly the grader is. Okay. Okay, and now next question: how steep is the hill? Well, again, how steep the hill is means how steep is it as I go uphill, directly uphill, namely what is that maximal directional derivative, and the answer is the magnitude of the gradient. So notice this is very plug and chug. You compute the gradient, you figure out what direction it points, you figure out what its magnitude is. That tells you which way is uphill, and it tells you how steep the mountain is. All right. Yeah. Okay, here's another cool thing about gradients. It's going to take us a minute to work up to it. I'm going to consider a level set of a function f. Now, very importantly, I just pulled a fast one. Part of your job as students is to always keep an eye on this sort of thing. I'm just going to point it out because it's so stark here. Here, we're looking at a surface described by a function f. Here, we were looking at a surface described by a function f. They're totally different because this one, the surface is the graph of a function of 2 variables. This one here, very importantly, this surface is a level set. of a function of 3 variables. So totally different. We're going to have totally different interpretations of all of our calculus. Right, so anyway, heads up, right? Now, again, I'm making a big deal out of it here, but in general, I might not. And outside of this class, certainly the context very often just will not, right? So y'all have to be super heads up about this kind of thing. Okay, so that said, I'm going to make an observation. Now, this is just an observation, but if you are at this point right here, well, that point is on my surface. And let's see here, my surface, my surface is a level set, so I can tell you what the value of f is at that point. It's c, because I'm on the level set defined by f equals c, right? Okay, now, what if I were moving along a certain path here where the entire path is in this surface? Well, the value of f is equal to c at that point, because it's on my level set. It's equal to c at that point. It's equal to c at that point. It's equal to c at the point I'm at. It's equal to c there. It's equal to c here. It's equal to c there. The value of function f is c everywhere along this curve, right? Which means f is not changing as I move along this curve. Which means f is not changing as I move tangent to the curve. As long as I am moving tangent to the curve, I am in effect moving along surface. As long as I am moving tangent to the surface, I am moving effectively along a curve in that surface where f is not changing. And so that rate of change of f is 0, and we don't even need the curve anymore. As long as you're moving tangent to a level set, the function's not changing. Okay, so fine. Now here's the nice interpretation. So let's not forget about the fact that df ds is a directional derivative. Directional derivatives are computed by this dot product, and that means that, well, if df ds is 0, that means that this dot product here is 0. Yeah? And if that dot product is 0, well, that's a geometric statement in effect, right? Geometrically, dot product equals 0 means 2 vectors are orthogonal, and so let's interpret that. For every one of these tangent vectors, any vector tangent to the surface, any vector parallel to the tangent plane, therefore, the gradient's got to be perpendicular to all of them. Now, how is that possible? What direction could the gradient of f possibly point to be orthogonal, right? Orthogonal to all of those tangent vectors, and really the only possibility is that it's got to itself be perpendicular to the surface, or 0, right? But that's silly. So generically, perpendicular to the surface, in particular perpendicular to the level sets. So this is the really nice interpretation, powerful interpretation. Gradients are always orthogonal to level sets. How are we doing? Everybody follow that? Yep.
So even if the surface is like kind of, so I guess over the gradient at each point is like different.
Yeah. Oh, yeah. So this is at the point in question. So a great point. Let me just amend the picture. So at this point, that's some point A, and I can find I can compute the gradient of f at that point A, and that vector will be perpendicular to the surface at that point. Now you bring up very reasonably that at a different point, like over here, at that point, well, yeah, I'm going to get a totally different gradient vector. which means I'm going to have a totally different direction, which it better be because it's a totally different part of the surface that it needs to be perpendicular to. Does that make sense? Yeah. So this is all at a given point. Yeah. Another thing I want to be emphatically clear about when I say, and let me do the color coding again, that gradients are perpendicular, to level sets, I should be clear. Gradients are perpendicular to level sets of the same function, right? So if you're looking at a graph of one function, you can't relate that then to a gradient of a different function or vice versa. It's got to be the same function. Does that make sense? Okay, so that is going to segue nicely into this next example. Okay, we're doing good. So this is going to be a different solution to a question we already know the answer to. Mathematicians do this a lot. We revisit questions that we already have one answer to get multiple points of view on the same thing. It's a really valuable general practice, I'll say that. So, here we go. We've previously talked about, suppose you have a graph, and I emphasize graph, right, of some function, little f. And suppose you want to find the equation of the tangent plane. Well, we know how to find the equation of the tangent plane. You take that function, you do the linear approximation, and then the tangent plane is the graph of that linear approximation, right? Old news, that's early chapter 2. Wrong color. The function f that you're looking at a graph of. That's your strategy. Okay, so now you can do that. And again, if your interest is the answer, then that's fine. But again, our interest is ideas. What other ideas can we throw at this? What other point of view could I take to answering this question? How else might I find the equation of that tangent plane? So I'm going to make this old observation that you can move terms around in an equation. Now again, that's trivial algebra. Basically nothing happened. Right? Yawn. And yet, check it out, I am now looking at a level set instead of a graph. So, and of course now that's with a new function. This is a new function called g, right? But this question that came to me as find the tangent plane to the graph, I can now say phooey on f. I don't need f. I don't even like f. That was part of a graph point of view on things. I want to view this surface as being a level set. This surface now being interpreted as a level set. Now, very importantly, again, not that function, not f, right? We've got this new function for which this surface is a level set. How now would I find the equation of a tangent plane to a level set? And there's a really nice tool for doing this, and that is, as we just discussed, gradients are always perpendicular to level sets. I have a level set. I can find a vector perpendicular by computing the gradient. And of course, that vector being perpendicular to the plane I'm interested in, I can call that my normal vector. And once you have a normal vector, it's all over but the shouting. Right? And y'all know how to do equations of planes when you have a normal vector. So really nice point of view. Notice that in this argument here about level sets, I didn't have to make any references to linear approximations at all. So very different point of view. I'm going to leave the algebra at the end here as a perfectly doable exercise for y'all to make sure that you're clear on where these formulas came from. It's a nice little quick thinker, right? And then make sure that you can plug in appropriately to the algebra. And then there's a little bit of an algebraic rewrite here. No big deal. y'all can multiply that out. And notice, by the way, you get to the exact same answer. You'll recognize this is the linear approximation, and here we're looking at the graph of the linear approximation. So same answer, as well we'd better. Different point of view. Okay. All right, there's an example here. I think this is a very readable. I hope you'll find this to be a useful sort of rubber meets the road example of what we just talked about. Let me just point to the key points. Notice I did the same little trivial algebra that turns what came to me as a graph of one function into a level, not the right color, a level set of this now new function g. Right? This is kind of the key step. That you want to make sure that if something comes to you as a graph, and if you want to use the calculus of level sets, you better rewrite that graph as a level set. Identify what is this new function g, whose level set you care about, right? And then that's what you apply the calculus of level sets to. Namely, that's what you take the gradient of, etc. Also, notice I give you a point 2, 1. That's a point in the plane. We're not interested in the point in the plane. We're interested in the point on the graph. And so you've got to figure out what is that corresponding point on the graph. Just like we talked about in that previous example. Again, make sure you're comfortable with that. Think through the details. Okay, so now we're going to move along to a new idea. This is arguably a point of view on the chain rule, and we'll get to that chain rule aspect of this in a minute. But I want to first just come at this as a totally new question. Namely, I have a curve. By the way, the curve that we're going to be looking at, I'm going to assume it has come to us as a level set. You better make sure that it is. If the curve comes to you in some other form, and for this context, for what we're going to do here, we need it to be written as a level set. So it comes to us as a level set. And that said, looking at a level set curve here, question I want to ask is, looking at a given point, does the curve look like a graph near that point? Now, what do I mean by near that point? That's what we use this word locally to refer to. Locally means I'm going to restrict my attention to a nearby, what we call a neighborhood of the given point. That neighborhood can be as small as you need it to be for your purposes, right? So assume that it's arbitrarily small. Okay. So when I say, can this curve be viewed as a graph, or can I view y as a function of x, even though it didn't come to me that way? Locally, again, means that I am going to ignore all the rest of the curve. I don't care about what the curve does outside of my little local neighborhood, and I'm only interested in locally. So therefore, just that little part of the curve there. Just that little green part of the curve. And looking at that little green part of the curve, is y a function of x? Does this pass the vertical line test? In other words, why, yes it does, no problem. Flying colors. So I can view, locally anyway, I can view y as a function of x. Everybody on board? Okay. Now, a lot of people will get it wrong with the next version of this question. Suppose I'm interested in, again, locally, what's happening near this point. And a lot of students move a little bit too quickly and say, can we pass the vertical line test? And they do like this, and they see, oh gosh, well, yeah, no, that failed the vertical line test. And so they go with the answer no, but that's the wrong question, right? The question here, when we say locally, what we mean, again, is that I'm only interested in that part of the curve. I'm only interested in this little bit of the curve. And for that little bit of the curve alone, ignoring the rest of the curve. The rest of the curve is not there for our purposes. Does this pass the vertical line test? Why, yes, it does. No problem. So, yes, for that point as well. Everybody cool so far? Okay. So, lastly, let's, again, same question, locally around that point. Locally means I'm only interested in this little part of the curve. And does that little part of the curve pass the vertical line test? And no. Right? Even ignoring the rest of the curve, of course, because we're looking locally only. Even ignoring the rest of the curve, we're going to lose. I'm going to hit that twice. So therefore, for this one, no. Y is not locally a function, not even locally a function of x near that point. Everybody see the problem we're interested in here? So this is the distinction that I want to worry about. Now let me dwell for a moment. Why would I ever care about such a thing? Well, because this is what we need to make sense out of the idea of dy dx. I can talk about what dy dx is at that point because, well, yeah, because locally y is a function of x, and if y is a function of x, I can talk about the derivative of that function of x. And here, for example, now there's a different slope there, but I can ask, what is that slope? And I can talk about that as the derivative of y with respect to x, because y is a function of x. At this point, I cannot. And a lot of students get this wrong as well. A lot of students would say the derivative is infinity or something, and it's not infinity. Infinity is an answer. My point here is that you can't even ask the question. You can't even talk about what is the derivative of y as a function of x, because it's not a function of x, right? Very importantly, derivative is something we do to functions. You cannot take the derivative of a bicycle. Doesn't make any sense. It's not a thing, right? There is no derivative to even ask about, much less have an answer to. Okay. All right. So, so we got to be careful about this. Now, here's just for context. Here is a scenario that y'all may have seen in the past. I saw this when I was in high school, and the question was, okay, well, if we have a circle, right? And if let's write this down, x squared plus y squared equals 1. And the question is to compute dy dx. And so what they do is they say, okay, well, we're going to view y as a function of x, and thereby immediately write down, I'm going to do this in red to emphasize that this is bogus. They write down, okay, let's take the x derivative. So we get 2x plus 2y dy dx equals 0. Y'all seen that before? They call this implicit differentiation. I can't do that. I have assumed here, right, the act of writing down this right here assumes that y is a function of x. And you know what? It is in a lot of places, right? There, yes, there, fine, there. We're all good at those points. At each one of those points, yes, y is at least locally a function of x. But not here. And again, it's not that dy dx is a meaningful concept and the answer is infinity. No, it is not a meaningless concept in the first place. So you can't even write that down until you have established that at the point you're interested in, that y truly is, in fact, a function that you can therefore take the derivative of. Okay, all right. So, So a lot of high schools are really sloppy on this point, and, well, what are you going to do? Okay, but let's be more careful about this. And here's the argument, how we handle this, by the way. Here's what a problem looks like. Oh, I'm sorry, I forgot to hit the button there. Okay. Here's what a problem looks like. The curve is in the process of wrapping under itself. That's why we fail the vertical line test at a point like this, is because at a point like that, because it's wrapping under itself, that's why we're going to have this double hit on that vertical line test. Does that make sense? I point out, by the way, that's what I'm going to call the problem. That's where all of our bad news is going to come from, is the curve is in the process, at the point in question, in the process of wrapping under itself, some form or another. Notice that is synonymous with a vertical tangent line to the curve. Notice I didn't say derivative. I don't assume the existence of a derivative. But I can talk about a tangent line, and I can talk about that tangent line being vertical. And, that means that the level set is basically vertical there, which would mean that the gradients being perpendicular level sets, would have to be horizontal. Yeah. Very importantly, quick side note, gradient of the function whose level set I'm looking at. Very important. When I say gradients are perpendicular level sets, if you're talking about the gradient of the same function whose level set you were looking at. Right, so in this case we are. Which, by the way, is why I was so emphatic that the argument that we're going to do here requires that we're looking at level sets. Yeah.
But isn't it not a function?
No, y is not a function of x, but f is a perfectly So this is a perfectly reasonable function of two variables. The big question is to whether this can be viewed locally as a function of just x.
Okay.
Yeah. No, it's good concern. And that's why this material is so confusing, is because there really are two separate functions playing two importantly different roles. Yeah, totally. Okay, so wait a second. So I need the gradient to be horizontal. Wait a minute. How do I compute the gradient here? What is that? The gradient is the partial of f with respect to x, partial of f with respect to y. What does horizontal mean? Well, horizontal means that component has to equal to 0. So the y partial would have to be 0. Right, so what we have here is an argument. This argument that goes from, we have a problem which always looks like that, and I concluded that if that problem happens, then the y partial must be 0. And now I'm going to pull a standard move in math, and that is to write down what I call what is called the contrapositive. And the contrapositive says, you turn it around backwards with negatives, right? And I think it's pretty intuitively satisfying. If problems always make this y partial 0, well, if the y partial is not 0, then there can't be a problem. And this is our big test. This is the quick and dirty, which is all we're going to do in this class. Again, I don't want to be all about the rigor in this class. This is our for single variable calculus purposes. In other words, looking at curves in the plane. You take the partial with respect to y. If it's not 0, no problem. Go ahead and do all of your high school implicit differentiation calculations that you want. It's all good. Just make sure that you've checked that condition. Okay, now that cleans up high school calculus. Here's the three-dimensional version of it. Suppose I have a level set this time, level set of a function of 3 variables. So we're looking at a surface. What if at various points on this surface I want to know, can I view z as being a function of x and y? And again, locally. So z locally a function of x and y For example, I might be looking at a point like this. At that point, locally, looking at this little piece of the surface, does that pass the vertical line test? Why, yes, it does. No problem. Don't worry about this stuff down here. It's not local. Right? So, yeah, no problem at that point. But you can imagine there are points where this is going to be a problem, namely at points where the surface is in the process of wrapping under itself. And that's a loser right there. Right? At that point, you can't view Z as being a function of x and y. It wouldn't pass the vertical line test. That's not a graph of a function. It can't be. Morally equivalent reasons. And then we make this observation that, well, wrapping under would mean you have a vertical tangent plane. A vertical tangent plane would mean that you have a horizontal gradient. And a horizontal gradient, again, you write down the formula for the gradient, and what that would give you is the z partial would be 0. And then again, you can take the contrapositive. If the z partial is not 0, then there is no wrapping under, there's no problem. Okay. All right, so here's the theorem in general, and this is copied pretty much straight out of the book, as I recall. The key point to notice, a couple key points to notice. We start off with various variables, all understood to be independent. They're all inputs to some function capital F, one of whose level sets we care about. But it comes to you with all of the variables independent. We would like to take one of those input variables and view it locally as a function of the others. Can you just do that? Well, problems. And so basically this argument here, you just generalize this argument. We can't draw the picture in higher than 3 dimensions, of course. But morally, a generalization of that argument tells you what the test is, and that is as follows. Whatever variable you want to view as a function, take the partial with respect to that variable. And if it's not 0, then no problem. That's the general test. And just to emphasize, you always take the partial with respect to the variable that you want to view as being a function. Okay, so let's see this in action. See how we're doing on time here. Okay, good. Okay, so I have here a surface, and I'm interested at a certain point on that surface, and y'all can confirm that that point satisfies that equation. At least I hope it does. I think I'm pretty sure it does. Check me on that. Pretty sure it does. So I have a point on this surface, and I want to know near that point, and again, there's this word locally, right? Can I view x as being a function of y and z? And notice I'm taking them out of alphabetical order, right? And this could go either way, whatever, right? I want to view x locally as being a function of y and z, and so we have a test for this. And again, whichever variable, wrong color, whichever variable you want to view as being a function, that's the one that you take the partial with respect to. I want to view x as being a function, so I take the partial with respect to x. Is that cool? Yeah. Okay, well, so then it's all plug and chug from here. I guess I better be careful about one other thing. Let me not go too quickly. What do I take the partial of? A lot of students move a little too quickly on this. A lot of students say, okay, well, I'll just take the partial of this. No. That's an equation. That's not a function. That equation could be written in various different ways. I could take some of the terms, move them over to the other side, and toss things around, exponentiate both sides of the equation. I can make this all kinds of different forms, right? What function specifically do we choose? Well, we choose the function for which I'm looking at a level set. So again, very important that we are looking at a level set of something. And I can see that this is the function whose level set I'm looking at. So that is the function of which I take the x partial. Is everybody good? Okay. All right. So then it's just details at this point. So you compute this partial where you get this formula. Don't forget we're interested in this point. So that's the point that you plug in. That's what this notation means. That vertical line just means I'm plugging in that point 1, 2, 3. And when I plug that in, I get this value, which is not 0. And so we're all good. Yes, it is. Yes, x is locally a function of y and z. All right. Okay. At which point you can do all your good old regular implicit differentiation. Now, what we have here is a point of view on how to streamline that process, and it gets us down to a formula, and I can imagine what you're thinking is, that looks kind of hard. That looks kind of intricate. There's a lot going on there. And it is, and so I'm not going to walk you through that. We could, but I don't think it's a good investment of time. What I'm going to do instead is point you to this, what I'm going to call the alternative diagram here. And the alternative diagram is, morally equivalent to what I have written up here. So the reason I hesitate on this is that this diagram right here doesn't satisfy the rules that I gave y'all. Right? If you're going to use the chain rule to talk about the derivative of compositions, etc., diagram's got to satisfy certain rules. This doesn't. So I am going to encourage y'all to feel uncomfortable about this, about the little fast one that I'm pulling here. And I'm also then going to ask you to trust me that in this case, what I'm about to write down works fine. And in this case, nothing's going to go wrong. Even though, yes, kind of, I'm breaking my own rules here. Right? So, okay. All right. So the big idea, again, is that we're looking at a level set of some function f, which means that this function here is not allowed to change. It's it's momentarily constant. So if I ask what the derivative of that function, how much does f change? Well, f isn't allowed to change. The derivative is going to have to be 0 because it's a constant. It has to stay a constant. And the question I want to ask is, supposing that I have already established that xi can be thought of as a function of the other variables, if in fact it has been thought of as a function of the other variables, how would I compute, for example, let me leave that there, how would I compute this partial derivative? What's the partial of xi with respect to xj? How would I compute that? So the big idea is that, well, let's just kind of compute the derivative of everything in this picture with respect to xj and see what happens. And, well, we've already agreed what happens to f. F is not allowed to change in total, so that derivative has to be 0 altogether. And I can also count different paths by which xj's changes can contribute overall to f's changes. And one path by which change can happen is, well, xj's changes will cause xi to change, and xi's changes will contribute to f's changes. There's one of my paths. But then there's also another path by which xj changing will make f change, and that is just directly. So these are the two different paths along which changes can propagate. And along each of these paths, there can be actual changes. But in total, that has to add up to 0, because that's the whole deal with f. Again, f is a constant because it is the function whose level set we're stuck on. And so with that written down, you can now just do a little bit of algebra and solve for partial xi with respect to partial xj. In other words, the derivative you're looking for. And here's your answer. And conveniently, y'all can just use this formula. Works just fine. Everybody good? Yeah, question.
How come you wrote not good earlier? Like for this, for the alternate diagram? No, you like wrote it. Or you drew like a frowny face. Like.
Yeah. Oh, yeah. No, okay, I got you. Yeah, because so I gave you all that whole speech back when we were talking about the chain rule and intermediate variables, that your diagrams have to follow certain. I mean, they've got to represent the composition of two actual multivariable functions. And here, oh gosh, I don't know what that is.
Okay, so
it's
you
just,
would prefer to do the one before.
Yeah, that's right. So the purpose of this up here is that this really is, okay, I see a function there, and I see a function here, and I see that what comes out of the one is what goes into the other, and there's no confusion. So this is a clean diagram here, and that's, you can write all the stuff down. It's just bulky and clunky, and this is just kind of the cut to the quick punchline, streamlined version of that. And yeah, it breaks my rule, but also it's fine. Is that cool?
Yes.
Yeah. Okay. Good question. Okay, so now I have a bad news, good news thing here. Here's the bad news. A lot of students will notice that and that appear to be the same, and it's as if those cancel. And let's see, the denominator of my numerator is the denominator, and but wait a second, the denominator of a denominator is the numerator, and so a lot of students figure, hey, that's why this works. And by the way, no minus sign, so let's just throw that away. And this is 100% garbage nonsense, right? As previously discussed, it's very unfortunate, and I wish it weren't the case, but this thing that we write as a fraction is not a fraction. This is not a fraction of independently defined things. So there is no cancellation here. So that argument that I just gave you is nonsense, right? So that's the bad news. That if you think of this in the wrong way, you will get a dramatically wrong answer. This, by the way, is why I make the observation down here that minus sign is so important. This minus sign, right there, that one little minus, most important minus sign in the course, perhaps. Case could be made. That's the only thing that distinguishes a perfectly valid formula that if you were to write down, I would assume the best and figure, okay, well, this student understands implicit differentiation. That minus sign is the only thing that distinguishes that from 100% garbage nonsense that if you were to write down, again, without the minus sign, I would have to conclude this student has written down what appears to suggest that they think that you can cancel the DFs. In other words, the student has absolutely no idea what's going on, right? So that one little minus sign, that's the only thing that's the little sliver of distinction between full credit and garbage nonsense. So don't make that mistake, right? That's all I can do is beg you, please don't forget that minus sign. You gotta have the minus sign, or else your work is. I have no evidence that such a student gets it, right? Now here's the good news. The good news is, well, first bit of good news, it's easy to remember, that little minus sign, right? Nothing to it. But more to the point, this nonsensical rule about these canceling, which is absolutely wrong, and this going there, and this going I wanted the color. This going there. That little rule other than screwing up the minus sign, right, is a very handy way to remember this formula. It's very convenient. So it's kind of garbage. So it sure is convenient garbage, though, right? And so why does this matter? Why can't we just memorize the formula as is? And that's because the variables, what f is a function of, will not always be called exactly these things. Sometimes it'll be x, y, and z. Sometimes it'll be p, q, and r, and s, or whatever, right? And so just remembering that the faux cancellation, other than the minus sign that it misses, the faux cancellation will always make this work. It's super handy. So if we return to the previous example here, and keep in mind we've already established that x is locally a function of y and z. This is the same example we just looked at. If I then ask the reasonable question, this thing that I now know is a function, how would I compute its partial with respect to z? Oh, okay. Well, you want to compute that partial? Well, no problem. That goes there. This goes there. Don't forget your minus sign. Super emphatic, right? I mean, really don't forget that minus sign. Oh my gosh, so important, right? And then plug and chug. Okay. All right, let's see. How are we doing on time? Did I lose? I lost track of time. I'm sorry. Okay. Anyway, we're done with this section here. Little warning. Make sure to read the warning. And we're done now with Chapter 2. We'll be picking up with Chapter 3 on tomorrow. Y'all have a good one. See you later. Okay, let's see. Don't forget to, if